Boa tarde. Já estamos muito atrasados, então eu vou ser bem breve. Tenho que introduzir o doutor Josué, ou simplesmente Josué. Josué é um doutor muito jovem. Isto, ele entra naquela definição da FAPESP jovem doutor, que é, acho que 5 anos, né? Porque defendeu há 5 anos atrás. A, sobre a short view, não tão short que parece, né? Que vocês podem ver. Então, eu não vou ler tudo isso, só queria dizer o seguinte, ponto importante. Josué começou como um típico estudante brasileiro, acho que estudantes brasileiros que estão aqui, escola estadual, né? Graduação e pós-graduação na Universidade Unesp, Universidade Brasileira, em matemática e física, só que defendeu em 2018, né, seu doutorado. Só que nesse meio tempo, ele conseguiu desenvolver pesquisa, fazer estágio, se comunicar e aprender praticamente em 4 continentes, né? Só faltou Austrália, faltou
Não, e a Europa, não podia ir para a Europa. Mas
Europa.
a Ásia, América do Norte e América do
Do
Sul.
Sul, África, acho que Israel
É,
também pode
é,
ser. Então, está faltando África, está faltando
Antártida.
Austrália e Antártica, onde ele não fez o trabalho dele. E eu acho que estudantes que estão aqui, que estão interessados, seriam interessados em ver quais são esses caminhos para percorrer, forma como percorrer esses contatos, procurar os contatos, saber como é, quais as dificuldades. Vocês podem depois conversar com o Josué sobre isso, que seria realmente muito proveitoso. E a área de interesse dele, como ele consta próprio, mecânica celeste que é apresentado por nosso grupo aqui no IAG, astrodinâmica, espaço exploration, space exploration, missões espaciais, astronomia dinâmica e história de ciência, que ele realmente tem as lives, né? Está prestando bastante serviço nesse, e muito importante parte história de ciência. O, o que eu queria dizer, que eu já disse para ele hoje, que eu vejo o futuro dele aqui no Brasil, apesar que agora ele acabou de sair do Japão, né? Passou aqui, ou vai passar aqui um mês no Brasil e já é contratado lá nos Estados Unidos, em Colorado, como professor associado, né, para trabalhar lá. Mas eu vejo o futuro dele aqui no Brasil, realmente. Eu acho que no design of space, eh, animation, sei lá, design, sabe, aqueles mapas de metrô que estão desenhando para o sistema solar, para o espaço, isto é, usando a mecânica celeste para desenhar os caminhos onde a força gravitacional, não o combustível, não, nada disso, né? Força gravitacional vai levar a gente lá para fora dos confins do sistema solar e mais adiante. E é isso que ele vai contar hoje para a gente. Tá?
Muito obrigado, Tatiana, pela muito bondosa introdução. Para mim é uma honra estar aqui de novo. Em 2017 eu apresentei um seminário aqui para o Grupo Dinâmica, mas agora um grupo mais geral. A minha esposa é egressa da USP, ela fez doutorado na Faculdade de Educação, mas eu sempre falo para ela, o meu sonho era ter estudado na USP. Né? Estudei na Unesp, que é uma universidade irmã, tenho períodos aí no ITA e no INPE também, que são outras instituições públicas. Então estar aqui é para mim sempre um local de honra, né? O professor Silva é uma das grandes referências, está aqui. O grupo, a gente é fruto do trabalho que ele desenvolveu na área da dinâmica. A gente já está um pouquinho avançado no tempo, então eu vou avançar atualmente, né? Estou nesse período de transição. Cheguei esse mês aqui no Brasil, de um pós-doc na Agência Espacial do Japão. Eu estou indo agora no verão para assumi uma posição como professor assistente na Universidade de Colorado, em Colorado Springs. Eu vou falar um pouquinho... sorry, I should be in English, okay. Sorry for those that are foreigners. Thank you, Tatiana, for the invitation. Now I'm progressing to a new position as assistant professor in Colorado. But I just arrived this month in Brazil on a position as postdoc in JAXA, that is the Japanese Space Exploration Agency. We're going to talk about analytical and semi-analytical methods for celestial mechanics problems and space mission design. So we're going to see the power of some mathematical methods. They can help us to understand phenomena in the space, in the solar system, specifically in my case, and there are other applications in other types of systems. But also, and these tools are also very useful to design space missions. And I'm going to give some examples. A little bit about me, Tatiana, I came from Japan, so this is a little bit of my career. So apart from UNESP, I spent 2 periods of a sandwich PhD in Colorado Boulder and JAXA. Then I went to Israel, INPE, ITA, and I just came from also a visiting position in University of California, San Diego. Always working with orbital dynamics, dynamic astronomy, astrodynamics. I'm going to make a brief introduction because the audience is broad, so you're not supposed to understand the difference between the things, celestial mechanics and space flight. So celestial mechanics is the area in astronomy, in physics, that studies the motion, is the mechanics, that studies the motion of objects in space. But this is the foundation for aerospace engineering in terms of space flight, because we use in the applications for space missions, in the motion of satellites, all the laws of physics that since at least Newton, when he started to model mathematically the motion of the objects in space, we use all these foundational works that were developed by Newton, Lagrange, Laplace, and so many others, that provide the framework where all the other operations that a satellite can perform in space in order to achieve the observations in the regions that we want, to maybe land an object in the surface of a planet, of a moon. So celestial mechanics is the foundation that every project of a space mission needs to be built upon, because if you cannot plan such observation of an area in a space object if you cannot achieve that area. So we need first to understand if we are able to reach that region in space to make those observations. For example, we have the case of New Horizons. We have a flyby. It passed by the region of Pluto and Charon, but it was only possible because they could design the trajectory using the gravity of the planet to make it faster. Otherwise, it would take them so long to reach there. And the understanding of celestial mechanics was fundamental in order to understand the interaction between the particle or spacecraft, or whatever you can name it, and the gravity of the planet that used the Air Force to accelerate the spacecraft towards the encounter with Pluto. So, and not only that, with this background, we can plan and design so many applications that are part of our lives today. So, forecasting, agriculture, GPS, everything that's necessary for modern life is based on space technology. So this is also important to explain people the importance of investment in science, in space science, in our case that are interested in this, because this is what we use to rule the life in the modern society. We cannot live without it anymore. So investing in this is investing in the quality of our lives, in improvement of the technology that will make the life better, will improve the food production. This is what India did with using satellites. They are able to harvest more efficiently the land and produce more food because they have a big population. All these things are fundamental for this subsistence of human life, especially now that the population is growing. We need to optimize this stuff, and space technology is very fundamental. But also it's important to build technology that will help us to understand better the universe, to help us to reach, maybe we never reach, just using instrument. We need maybe philosophy to help on that, but this will make it with space technology, space exploration, understanding of celestial mechanics. We can put telescopes like James Webb in that specific position that we call the L2 point, the Lagrangian point, behind the moon, that was designed using celestial mechanics. And there's a reason for putting that satellite that is able to produce so stunning results as we are seeing in terms of at least galaxy formation. James Webb is using this foundational works in order to understand better the universe. So this will help us to understand who we are, where we came from, where we're going to. The meaning of life can be understood better using this understanding. Starting back, the space trajectories, they are based, usually the classical problems when Newton published his masterpiece, that is the book Principia, in the solution of the gravitational theory, he put an object around the Earth, but you can generalize that to two objects. In the types of trajectories that these two objects moving around each other, actually around the center of mass of the system, the barycenter of the system, these are the types of trajectories that these two objects interacting gravitationally can have: circle, ellipse, parabola, and hyperbola. The thing is, as we have perturbations in the universe over the motion, technically we don't have circle, because they will always be deviating. The majority of the trajectories that we observe, especially the planets or the asteroids around the sun, or satellites around the planets, are ellipses. We have comets that, for example, they have a trajectory similar to parabola or hyperbola. They pass and they go. So, but the majority of the cases of my interest are elliptical cases that are the majority of the studies that we perform. These are the variables that describe the motion. So we have a reference here, the reference plane, that is the blue plane, and the orbital plane is this yellow one, and we have here variables that describe the motion. So we have three variables that describe two variables that are the semi-major axis that gives the size of this ellipse, but the same can be for parabola or another object. We have eccentricity that gives the shape of the orbit that is more circular or more eccentric, and we have inclination that shows how inclined or tidal is the plane in reference to the inertial plane that we choose. And we have these other these two omegas that are longitude of the nodes and the argument of pericenter that rotates the reference direction of the plane according to a specific direction that we use as reference. And the true anomaly that describes the motion of the satellite or planet or moon in the orbital plane. These are just fundamental things. But we know that in practical terms is that real life is not just two bodies moving in space. We have so many other perturbations that take place. And for example, if you think about a satellite moving around the Earth, this satellite is under the influence of GM is the gravity of the Earth. So this plot here shows the altitude of the satellite, and this is the magnitude of the force, the acceleration that the object will suffer. So we see, of course, the attraction of the Earth is the main contribution, but you also have other perturbations. For example, J2, that describes the flattening at the poles of the Earth, is 10 times bigger than the other deformations in the Earth. And for example, around the region of 36,000, that is around the geostationary region, where the satellites have an orbital period of 1 day, we see that the forces of the sun and the moon start to be of the same order of magnitude as the flattening at the poles. So if you are in lower altitude, maybe J2 is the main force. You can model majority of the system using that. But if we start to go up, the order perturbations that exist in the system needed to be accounted. And we have atmospheric drag, we have also solid radiation pressure, the albedo, the tidal force, relativity also. We have all these forces. So modeling the motion of an object in space, we make jokes that we will always have worked forever because each system in the universe is unique. So we always need someone to be developing a modeling of that system individually for each case. So, and these are some illustrations of this. So in my specific case, applying this stuff to space investigation, for example, astrodynamics, celestial mechanics is what, as I mentioned, is the motion of the objects in space. But nowadays, with the advance of technology, and we can build artificial space objects like that are satellites and other equipments, we try to separate. So celestial mechanics is when we're talking about natural objects. And we're talking about the motion of objects in space that are man-made objects, we call astrodynamics. But the concepts are the foundational physics, the physics that is behind it is the same. When you apply these studies to natural systems, we can, for example, in my case, I've been specializing in studying planetary satellites and other minor bodies and planets in the solar system, for example. If you apply for artificial systems, for example, we can design orbits for a space mission. We can study dynamic stability for observations of a certain area around a planet, for example. And you can also apply and use all those perturbation effects about, today we're talking about space sustainability, so we think how to use those environmental forces that exist in space to remove space debris and clean the space environment. Another area that goes more to mathematics or physics interest is dynamical systems. So understanding this phenomena, we can study chaos and apply some Hamiltonian perturbation theory. Okay, these are some illustrations of what we can do. For example, I'll give you one example. For example, we have a class we call the three-body problem. There's now the series that is being popular, but what they're talking about is actually not technically the best representation of this. But the thing is, we have a central body that can be, for example, the sun, and or for example the Earth, and you have here the secondary body, can be a spacecraft or the moon, and you have the sun as the third body, disturbing. So actually this object will be disturbing the motion of this other one around the central body. But it's not just that. This central body has deformations. For example, C20 is what we call J2. Actually, it's minus C20, mathematically speaking, is what we call J2. As you can see, the difference in the color means in the red colors we have less mass. So it means the object is flat. The Earth is not flat. There's a flattening, but the Earth is almost circular. So is the order of 10 to minus 3 in the correction of the gravitational field. So it's like 0.1% in comparison if the Earth is a perfect sphere. And we have what we call C22, that if you see the different colors means we have more distribution of mass along one direction in the equator than another direction. For example, if we think about American football ball, we have more distribution of mass in the equator along one direction than in another. So we call, for example, it's like a ellipsoid. J3, you have different colors. It means we have more mass in the northern hemisphere than in the southern hemisphere. So these things are, and when we model the gravitational field of an object, this is also some that is common for people in geophysics, shown to geodesy, people that are interested in geodesy. They are interested in this because you can model in a series expansion, and if you sum the contribution of each one of those terms, we can have a very accurate description of the motion of the gravitational field of an object. So, for example, using do you remember that we have those 6 variables that describe the motion of the object in space? Remember, why 6 variables? Because, do you remember in physics, in order to determine the state of an object, the motion of an object, we needed to have the 3 coordinates of position and 3 coordinates of velocity. And with that, we can understand the evolution of this object in space. But these variables are not convenient. So we can, from these Newtonian equations, we can move to a representation in orbital elements. So we change just the representation of the variables in terms of position velocity to orbital elements that we can easily visualize and see they are trapped in this orbit. If I give you, the object is moving with 10 kilometers per hour south, are you able to visualize the motion? No, but if I tell you, the object has the orbit is, the centricity is 0, so you know it's trapped in a circular orbit. You already are constrained in the motion, you can visualize it. And these are the equations of motion. And these equations here were called the Lagrange planetary equations. And I'm giving here the form that is presented in the book of Kovalevsky, that is the PhD supervisor of Professor Silvio Ferraz Mello. And these are the equations, these are the gravity potential that describe the formation in the gravitational field of each one of these forces. And why is that important? Because these potentials, we plug in this function R. So each new force that we plug in, we just sum, and we apply the partial derivative, and you have the full expressions, and then we integrate the system. But the thing is, this is how we develop, in terms of series expansion, the perturbation of the third body, for example. I'm going to show an application of this. And additionally to that, we can decrease the degrees of freedom of the system if we have some phenomena, for example, small oscillations because of the perturbations that we call short period effects. They, for example, increase a lot the time of integration of the system. Because imagine that you are integrating the motion of the planets in the solar system. And you have Mercury, that has an orbital period of 80 days. And you have Pluto, that has a orbital period of over 270 years. What will happen? In order to get accuracy in the integration, we needed to decrease the time step, the step of each integration, to a few hours to get accuracy, to get the accurate prediction of the orbit of Mercury. But imagine what will happen if you needed to integrate for billions of years. The evolution, the estimation of the position of Pluto with time steps of hours will take a long time. It will be very heavy computational effort. But if you remove the short period effects, we don't need it to account. We don't need to pay attention to be worried about these small oscillations. So what will matter here is the red evolution, and all these small oscillations that we will need to decrease significantly the time step of integration will not contribute more than just moving the integration to much more time. And additionally, you can decrease sometimes if we pick these equations and apply the average, you can remove degrees of freedom, and then sometimes you can find mathematical average mean solutions that can provide us expressions that approximate the real physical system. It means the following. We can see the coupling between the physical parameters in the system having a mathematical solution for that. So we can speed up the integration. We can find analytical, mathematical solutions for the problem. And after finding the solution, we have methods that are numerical or mathematical. We can recover these effects back, and we can have a very accurate description of the physical system. So it's very convenient to apply this method. So, for example, if you think, I know you are an institute, you have many studies about exoplanetary systems. For example, applying concepts of what they call Lidov-Kozai resonance, we call. This term is a contribution of Professor Tatiana in the literature, because in the past the work of Kozai was more known in Western world, but Lidov has published it 1 year before. So, and she said, no, we should update literature because Lidov did some contribution. The thing is studying the interaction between three objects. There is a term in the expansion of the gravitational potential that is able to explain how planets in exoplanetary systems will have retrograde orbits, and because the the classical expansion that we use is up to second order of the potential, is a series expansion. We presented the planets evolving in prograde orbits, regular orbits as we observe. But when we observe using our telescopes and space missions some planetary systems, they have planets that are in retrograde trajectory. And if we expand to more orders in the series expansion, the potential that we describe this effect here, these higher order terms in the mathematical expansion, if we integrate the system using these higher order terms, they will create the flip in the orbit, as you can see in that animation there. So we need this more fundamental astronomy, this celestial mechanics, in order to understand the phenomena we observe in the universe. For example, applying this concept, for example, for the moon Callisto, I try to investigate this because that phenomena that you call the Lidov-Kozai resonance, if you are in polar orbits, the attraction of the 30 body, for example, in our case, we have the moon Callisto, one of the Galilean moons, and you have the spacecraft in polar orbits, and you have Jupiter attracting. The attraction of Jupiter will create an oscillation in eccentricity, so the shape of the orbit will be elongated, and inclination. What it will cause, if the eccentricity elongates, the perigee, the pericenter, that is the closest point of approach of the object in orbit, will reach the surface, so it will have a collision. So the attraction of the 30 body, if you are in a polar orbit, will create an impact in quick time. This is what we call the Lidov-Kozai resonance. But if we are going to observe an object in space, we need to observe in polar orbits in the majority of the cases. Why? If you are in equatorial orbits, you have the object here. If you are in equatorial orbit, you can map. You have a certain limit of latitude you can observe. But if you are in a polar orbit, you map. You make one revolution, and the object rotates, and you map another slice, and then you can, as the body rotates, you are mapping different slices until you map the whole object. So this is the best. So we needed to maintain a spacecraft over there. But the plots in the top represents the majority of the cases. So the y-axis represents the orbits with 90 degrees of inclination, polar orbits passing through the poles of Callisto. But studying this phenomena, the resonance, I was able to identify some initial conditions for how you rotate, the initial conditions for the rotation, the position of the orbit, what we call the position of the pericenter, and the longitude of the nodes, how the orbit is rotated in a line in space, and I could find specific areas, combination of these initial angles, that creates some islands of stability. So for specific orientations of the ascending node and the argumental pericenter of the orbits, we are able to find orbits that inclination will never reach the critical inclination that creates collision. So no collision over time. So it was not known this. After that, there was a paper published that proved that Callisto is the only moon in the solar system that is able to have another moon. And these regions were mapped in this work. A proof of that the Kozai-Lidov resonance for the majority of the cases, this is inclination in the x-axis. So for different altitudes of orbits and for different shapes of orbits, you see that in the center of the plots, the orbits always survive a few hundreds of days. So in this case here, around 90 degrees of inclination here, we have the majority of the orbits colliding very quickly in a few hundreds of days. So you don't build a spacecraft that costs hundreds of millions of dollars, send there to survive 1 or 2 years. You want to extend the mission further, that's the most. But using the initial conditions that I found, the geometrical configuration of the system, simulating all these trajectories again, what happened with the orbits that are polar? They go to thousands of days. That potentially, and this is the mechanism, then they find that Callisto, that's why in these specific regions, Callisto can have even another moon. Would be called moonlet, or moon, sub-moon. There's a discussion about how you, after we find another moon, how you're gonna name it. But the thing is, knowing this mechanism, we can explain phenomena, even provide number. Okay, the scientists now they can design spacecraft using those numbers, and there you can have a spacecraft that will be safely observing for years and many years without any need of control or anything like that. And why is that important for us? As scientists, if we're in space and you want to be part of a space mission, and even people that are in experimental area, I want to propose an instrument. They say, okay, yeah, but how heavy is your instrument? Why? Because each kilogram costs tens of thousands of dollars. So providing these types of regions for the space mission, so if you can save control, we don't need to choose the propulsion system, we don't need more fuel to control. This is that we are saving space now for another instrument to get in the space. Applying the same ideas of investigations for we have next year, Bepi-Colombo mission is arriving to Mercury. I try to do the same. Let's investigate how is the stability of the orbits in polar orbits around Mercury. And I found that this asymmetry here in the initial condition, so a specific orientation of argumental pericenter of the orbit, we found this asymmetry here. But in this asymmetric region, we can make it the lifetime of the orbits explode and survive much more time. So in the other areas around here, we have a collision. Orbit's lifetime, you see 100 days, 200 days, 300 days. But around this specific value of argumental pericenter, we can so, of course, if Bepi-Colombo mission want to stay more time in this specific area that I analyze, they need to put with that value of argumental pericenter. And we find what we call frozen orbits. But the thing is, this phenomena is caused by the regular distribution of mass in the northern and the southern hemisphere of Mercury. So because Mercury has more mass in one hemisphere and another, we are able to find this stability region. So it's very interesting how, and the opposite can be the same. If we have a spacecraft that is behaving in a very strange way, we can maybe estimate how is the internal distribution of mass of that object. And this is how when we get to these numbers for that people in geodesy, geophysics use about the structure, the distribution of mass objects, they are using data from spacecraft that are performing those that navigation around the objects, and they do the opposite direction work. So in the case of Mercury, I also find this very interesting, that if we simulate the trajectories, these are again polar orbits, and the colors represent lifetime. If we simulate these orbits around Mercury, but we neglect that Mercury has a more elongated equator along one direction, so it's a small effect like American football ball. If we neglect, we have instability. But if we add that effect, that is more mass in one direction than another, we see that orbits will survive more time. So it means that the regular shape deformation along in the equator of Mercury helps to stabilize the particles or spacecrafts around it. So it is a geophysical effect playing a significant role in the space environment around the object. So with this stuff, we can do the same for asteroids and other, if we want to explore this. We can use this understanding order. For example, we have EthaSat 2 mission that is going to study the Atlantic anomaly in the magnetic field. And we have 3 satellites there, and we can use these perturbations and these 3 satellites, they needed to fly together. It's a formation flight. And using these perturbations, we can estimate the relative drift between the satellites, because they needed to maintain in a certain distance to perform the experiments in the ionosphere and also for geolocation. You cannot, we needed to predict these effects in order to mitigate, because if the satellites get too further from each other because of these perturbations, we lose the capabilities of the mission to perform. We needed to maintain within a certain distance for the accuracy of the experiment to be efficient. So, another example about solar sails. They're using spacecraft that we use solar light, so the photons from the sun, to propose the object. And as I mentioned that I found stable regions, we can do the opposites. So these maps here that I'm showing, just to summarize in one slide, these black regions are showing regions where you have a quick collision of particles around the Earth using effects of solar radiation pressure, the moon, the sun, the irregular shape of the Earth. And what it means, we are analyzing the geostationary region. It means that if we are able to move using different types of technology, lasers or spaceships that move space debris, old satellites, to these specific regions, if I'm able to move them to these specific regions, we have here the lifetime. So the time that it will take to go, in this case, we are removing to further distance from the Earth. But we can do the same to remove towards the Earth, and we'll burn in the atmosphere, and you can remove this space junk. So we can use the stability regions to maintain more time, but we can use also the instability regions to clean the space and remove our objects from any danger. There's another application for the case of studying the rotation, the orbit, the coupling of orbit, and rotational motion of binary systems. So we're discovering so many cases. How much time I have? Do I have? Okay. Yeah. So that is very interesting. We have so many missions that are interested in visiting, and we are being able to observe using our telescopes and space missions that these types of systems can be binary asteroids or binary planets or binary stars is much more common in the universe than we expected. So understanding how they interact physically is very important. So we can model these types of systems, for example, using this is the animation about DART mission that collide with Didymos. The moon of the main asteroid there is another asteroid. And now we have another mission that is going to be launched, I think, next year, Hera mission. No, later this year, actually. It's going to study how much deviation of the real trajectory DART will be able to cause to the system. This is also interesting for planetary defense. So how we model the relative dynamics? There are several ways to work with this stuff, but one way that using more classical celestial mechanics is using Hamiltonian approach. And we describe the evolution of the system in terms of the angular momentum of each object. So we have the rotational angular momentum, and you have the orbital angular momentum for each one of them, and you have the total angular momentum of the system. So we will build canonical Hamiltonian variables that are referred to the total angular momentum, and then we can apply geometrical transformations that can simplify, remove degrees of freedom of a system that initially was 24 degrees of freedom, and we can remove, applying some techniques to 1 degree of freedom, a simplified system that is able to mathematically predict the evolution of the system. I can give an example of this. So Hamiltonian with many variables here, we are gonna decrease these two types of intermediaries, what we call. You don't need to understand what is in there, but the important thing is to understand that applying these Hamiltonian approaches of celestial mechanics, here is a system that describes the 6 remaining variables of the system that describe the orbital evolution of the binary pair and the rotational motion of one of them. And the thing is, after we perform apply these techniques, we are able to reduce this. This is the evolution, this is the acceleration, and this is the position, the velocity. If we don't have this r, that is the position in the orbits, if we don't have the perturbation, the coupling between the two dynamics, this would be, if you remove this term here, we have 1. That is the two-body problem, the evolution of an object around another at the center of mass. It's a simple one. But the coupling of the forces in the system creates this. And this term is a constant. So it's a deformation of this evolution of the orbit because of the orientation of the secondary object. And but the great thing about this approach is this system, we can solve this pair of equations with two variables, two equations. We find a mathematical solution in terms of elliptic intervals. And after we replace them in the other equations, we can find a mathematical solution for all the equations of the system. Of course, there were simplifications, but from this simplified model, we can make the corrections. And the same applies for this system. We perform one extra simplification that is called parallax elimination. And with that, we can make the system integrable in terms of simple trigonometric functions, trigonometric quadratures. And after that, we use the Poisson brackets. So we have mathematical expressions from Hamiltonian theory. And we can recover the mathematical terms and find a mathematical solution with the simplifications that we removed being returned to the mathematical solution of the problem. And in dark colors are errors that are almost numerical. So we made a test for different, we performed tests. So the accuracy of these simplified models in comparison to the original models without simplifications. Here are plots describing the differences in the rotational axis, in the different shapes of the two pairs, the relative distance between the different eccentricities of the orbits. And these plots are the evolutions for all the orbital and rotational variables, and they are almost, in majority of the cases, very, very accurate. So the mathematical solutions that we have obtained are able to predict with efficiency and even much better. We can see the coupling between the forces. The gravity, the position, everyone is playing a role in the dynamics. We can visualize with the mathematical formulation. And finally, but not least, talking about MMX mission that I did some work with it. MMX is going to be we hope to be is going to be the first mission that is going to go to another planetary system, bring a piece of another planetary system. In the case is a flagship mission in the chart of JAXA to explore. This is the strategy that JAXA has to study solar system objects, but it's focusing minor bodies. I've been working with Destiny Plus and MMX, that is Martian Moon's exploration mission. Destiny Plus is going to escape in a low thrust trajectory. It's going to fly through the moon using the gravity of the moon to be redirected towards the asteroid Theta. I'm not going to talk about this today. MMX is going to go to Mars. I'm going to show you. It's going to go to Mars. And it's going to go to Mars. And we will study the Martian moons, but especially Phobos. And the plan is to land in Phobos, get a sample from the surface of Phobos, and bring it back to the Earth. We hope to do that even before the NASA Mars Sample Return mission. It's going to be the first piece from the Martian system. We are going to have the first piece of another moon. So it's going to be historic. It should be launched this year, but for security, for more tests of the rockets, H3, it was postponed to 2026 because we needed to wait the window to be launched to Mars every 2 years. We needed to wait. We missed the window this year, so we needed to wait until 2026. And we hope to bring back the samples back to the Earth in 2031. Initially, it was 2029, but with the postponement, we needed to move the date further. But the thing is, that's simple. Go there, land, and take the sample and bring it back. It just sounds simple, but it's very difficult. Essentially, you don't need to understand orbital dynamics. That's why important. But orbital dynamics showed that the mission needed to be redesigned. Why? The important thing about this map here is what you have the Jacobi constant is related to orbital energy. The thing is, the only things that can orbit Phobos, if you want to stay in orbit and observe, are the things that are inside these lines here. You see? It's a very narrow region, so you cannot orbit, practically speaking. So if Phobos has no gravity to capture the spacecraft to land, what we can do? What will happen if you are outside of these lines? So, for example, in these regions around here. what will happen is that the gravity of Mars will eject the spacecraft from the system, or you bring it to a collision with either Phobos or Mars itself. We needed to create a new strategy as we cannot stay around Phobos using the gravity of Phobos. What we do, we create a quasi-satellite orbit. And what is the thing? We have Mars in the center of the system, and you have Phobos orbiting Mars. But as you can see, you have an object here that is a spacecraft that's going to be MMX. As MMX is closer to Mars, MMX is faster. So it's the center. So it will make MMX go faster, and with that, we'll give escape, and you go to the front of Phobos. But then they will be aligned, but you have a momentum, and then MMX will pass. And as MMX will pass through Mars, be a bit further, Phobos will be fast, and then Phobos will. It's like in Formula 1 or any racing competition, it's like the X maneuver. This is a continuous, one pass each other all the time. And the only parameter you have to adjust to do that is the orbital eccentricity. You see, understanding the dynamics, the orbital dynamics, give us a strategy to plan. And what will happen so all the time, Phobos, MMX is passing through Phobos, then Phobos passes through MMX, and MMX passes through Phobos. What will happen if you are in a if you have put a reference system, reference frame in Phobos, you're going to see the spacecraft orbiting you in a retrograde trajectory. And we say is not a satellite orbit of Phobos because the center of the gravity is Mars. It's just a reference, it's a fake orbit. That's why it's not a true satellite orbit, it's a quasi-satellite orbit. And the thing is, and with that we can stay around Phobos using the gravity of Mars. So we will control. But we need to design the theory for these orbits. And this is what I did in Jackson. So, and we design, for example, we have a planar orbits. So you have only the motion x and y axis. And if we add a z component, we have these oscillations, and we have this. And now there's this discussion, for example. Do you remember about the higher altitude in terms of the poles of the object? You can map better. Instruments are being designed by people in NASA, in JAXA, in ESA that are partners of this mission. And we are from the flight dynamics team, and we want. Hey, what about putting some extra components? But that the instruments are designed to observe some certain regions. So, in this is the moment where flight dynamics help to even define how the observations will be done, and understanding this dynamics is important. But we needed to understand a model of this system and find if we are able even to have mathematical solutions that predict approximately this evolution is much better. So is it possible that the dynamics, this oscillation in the out of plane, the z component is affected by the motion here, the frequency here is affected by this? We need to show, if we have the mathematical formulation, how the variables are coupled to each other, we are able to understand this. And this is why we need a mathematical solution. This we developed, so this is just a scheme how it's going to be from the QSO, we'll call quasi-satellite orbit. The spacecraft will perform this maneuver, touch, sample, and escape, and go back to another QSO with higher altitude. This is the plan. This is a little bit of the geometry of the problem, and we create these different systems, but essentially we have the total system we call elliptic Hill problem, and we plug it then. But the interesting thing is how we describe this motion. We got the solution for the motion of two satellites flying together, but the difference in this case is Phobos has gravity that is not enough to capture, gravitationally speaking, but is able to disturb the motion of the spacecraft. And this is the problem. Mars always brings these problems, right? The atmosphere is not good enough to help to land, but is strong enough to create problems for us. And the same case for Phobos. Phobos has no gravity to help, but has gravity to create problems. And we modify the system, and then we describe in terms of Gauss rational equations. In order to obtain this, these are new variables that are not the classical position and velocity or even the classical orbital elements, but these are new variables that we create in the reference of Phobos. So this is something beautiful. We are not stuck to classical formula. We can create new variables that are used for different types of studies. We don't need to stick with one problem. We create new variables, and we updated. There were some ideas about these variables, but we updated in the literature. And these variables are, after we linearize the system, plug in the accelerations, the perturbation of Phobos in the motion of the spacecraft, we find a linearized model, and then we average, and we apply the technique of averaging, remove some angles of the problem, and then we find a mathematical first-order approximation of the motion. And then we need to test the quality of this. If we plot the evolution of our new variables in comparison to the classical Newton modeling, position and velocity, the error is 10 to minus 9. So our variables numerically are equivalent to the Newton formulation. But okay, but what about the solution, mathematical solution that we found after the linearization? We got this. LM is the linearized model. After these are the number of revolutions around Phobos, Phobos around Mars. Phobos is orbiting every month, so it's like 30 evolutions. So this is for a period of 1 month. Phobos is orbited 30 times. So, but the most important thing here is this is a period of 1 month of evolution. It's 3 orbits, about 3 orbits per day in our case. The error in our linearized model in comparison to the full model is only 1 mile after 1 month without any correction. Only 1 mile, so 1.6 kilometers. And of course, the mission will perform some control to maintain even closer, but the error is so minimal in terms of if you observe something that of the order of a few tens of kilometers. And these are some examples of, these are some, we have 6 equations, 6 variables, 6 equations, but each part of 2, we can find a system of differential equations that are solutions, and this is the relative error of these variables. Essentially, delta x is the shift of the orbit in the x direction. Delta y is the shift of the orbit around Phobos being centered along y direction. K5 and K6, they are relative to the angle in the angle is kind of the inclination of the orbit, and also the z component of the orbit in the Phobos system. So, but if we compare the error, it's very small. So the mathematical solution that shows how the thing, and why is it important? As I mentioned, with that approximation, we can find here, this equation predicts the frequency of those planes, those oscillations. And we just need to give the A, that will give the size of like almost equivalent to the altitude of the orbit around Phobos. If we're close to Phobos, you just put the value here and you can predict that frequency. If we are further, the frequency would be different. So we have a prediction, a mathematical prediction. But how accurate is this prediction? For if you put here the numerical, that is the complete model, and this is our theory. For orbits around 80 kilometers and above, our mathematical prediction is equivalent to the, but you can see physically how the parameters are completely set off just believing in a blind numerical simulation where you don't see how the physical parameters are interacting with each other. So for me, this is beautiful in terms of, we go to Louvre and see Mona Lisa, but I think if we're able to predict phenomena in nature with mathematics, I think it's a piece of art that as scientists we can produce for humankind. And with that, we can even guide now the team that will control. And we can maintain within a certain regime of X, Y, and Z. And what we have, if you constrain this, we are able to create algorithms that will design tori within, so the spacecraft can oscillate whatever with the whatever perturbations, but will constrained, will be bounded within this tori that maintains the quality of the observation. And we can apply even a small correction with this prediction, mathematical prediction, and we'll have, so from the error here, we can bring it back to the optimal solution, and we can stabilize around, so the shift between that the orbit was having because of the perturbation, with this mathematical prediction, we know how much control you can apply, and you can stabilize the orbit again and centralize around Phobos. Yeah, why this type of modeling? For example, this application for space mission, the celestial mechanics being applied for space mission design, but it is similar dynamics that we'll have for the case of Comoleva, the 2016 HO3 satellite, that is our most famous current quasi-satellite that is orbiting the Earth. You stay a few centuries around the Earth. It's the same type of dynamics. The only difference is the centricity. So understand how these types of objects can be captured and stay. You will be changing between modes of Hard-sourced orbits and other stuff. The same type of tools and dynamics can be explained, the structure of the solar system, capture and how the dynamics of asteroids evolve around the sun and other. In our case, this object is a quasi-satellite moon of our planet, but also can be applied to design space missions and observations and all the other things that are fundamental for us to get information. And we hopefully we'll be able to go to Phobos, get a sample, and then discover if Phobos and Deimos are asteroids that were captured by Mars, or they are the result of an impact that expel dust and other rocks in space, and after a few thousands of years, they got together and formed these two moons. Are they formed, or are they asteroids that were captured? Celestial mechanics is behind the modeling of the system, and also modeling the spacecraft trajectories that will help to understand the system. So I just want to show in this presentation, I'd like to, and modeling these dynamics, I was part with two friends and some colleagues from Colorado doing my PhD. We designed the first space mission for this asteroid, and we got the prize from the American Astronautical Society as the best project. And we designed, there's a whole thing, and this is in the UNESP news about research, and we got this prize. So we have potential to study astronomy and also space missions, be involved in space missions. These tools, if we are able to obtain them, provide us a broad range of possibilities and positions. We can teach in planetary science departments, we can teach in physics departments, mathematics departments, aerospace engineering departments. That's why I choose this topic, and that's why I've been following this career, because it's a very multidisciplinary topic, and I hope you like this presentation. If you have questions, please let me know. Thank you.
Thank you. Questions? We have.
Okay. Thanks for this presentation. It's very interesting. I have very naive questions because I am from a complete different subject. At the beginning, you show a plot of the forces or acceleration as a function of distance.
Yes.
Can you, I was curious to see there was albedo there. What do you mean with that? Because I get puzzled about that. I think it was...
Okay, let's go back here.
Yes, it was
yes.
yeah, there.
Yeah, albedo is the reflectance, because we have, when you talk about solar duration pressure, we're usually talking about the direct light from the sun.
Mm-hmm.
But we have also the indirect light that is reflected by the space object. So
I see.
if you have an object, so the sunlight reflects in the surface, and also will provide some extra photons that will accelerate or not. For example, in terms of, I can give an example about asteroids dynamics. We have two forces, a phenomena that we call Yarkovsky and Yorp effect. Have you ever heard about this? So if we model the evolution of the asteroids, for example, in the main belt, only using gravity and the interaction with the other planets, we are not able to understand the evolution.
I see.
For example, we have now the mission OSIRIS-REx that visited the asteroid Bennu, and they perform some estimations of the effect of solar radiation pressure in the surface of the asteroids. The thing is like this. You have the asteroids, and the sun is over there in the wall, and receive light, and there's heat being transferred, so energy. Mm-hmm. But the asteroid rotates. But when it rotates, it emits part of this energy in this direction. You create extra acceleration in this direction.
I see.
Of course, how this effect will only show up after long time, so hundreds of thousands or even millions of years. But this is even enough to modify the whole evolution of the system. Because if you try to, okay, this is the motion of this asteroid, and this is how, looking for the dynamics of the asteroids, I can predict where Jupiter was. No, you cannot even account for the Yarkovsky effect. But what is the Yorp effect? Similar, but the effect is not in the orbit, but is in the rotational motion. You receive light in one direction, and you emit in another direction, you create torques. Mm-hmm. But why is that important? In some cases, for example, binary system where the asteroids, they are close to each other, the ratio between the amount of effect that the orientation of the asteroid, the rotational motion, plays over the orbital evolution is the square of the radius divided by the square of the distance. Mm-hmm. So if you have two objects, and one has 20 kilometers of size, so the radius is 10 kilometers, and you divide by maybe 100 kilometers of distance, so you have maybe 1%, 0.1% every orbit of contribution that the orientation is giving extra gravity to accelerate or decrease the speed of the spacecraft, of the asteroid. Mm-hmm. In 99% of the applications, the satellite is a few meters, and the distance is thousands of kilometers. So square of meters divided by square of 1,000 kilometers is negligible. Mm-hmm. But for the case of binary system, this is not negligible. Mm-hmm. Or even if you have a small spacecraft around a very tiny asteroid, for example, Como-11, this quasi-satellite of the Earth, is 50 meters across. So if you are very close and you have a big satellite, the orientation of the satellite modifies the orbital evolution.
I see.
And understanding, discovering this phenomena that plays role in gravity, in these small, in very extreme regimes, and also the light is very fundamental in order to understand the evolution of the systems. So these are two phenomena, albedo and coupling between orientation, attitude we call, in orbits that usually people don't take into account. But with the new missions that we are designing for more challenging environments, we are discovering that this phenomenon is important.
Okay. Thank you very much. It was really clear.
More questions? Elizabeth?
Oi, Josué, eu tô aqui remoto.
Ok.
Eu não sei se você está me vendo, bom, mas não tem problema. Na verdade, eu estou na minha sala aqui no IAG mesmo. Okay, let me pose my question in English. Very, very, very interesting talk, by the way, Josué. And I want to understand a little bit better, because you showed the solutions. Of course, you have these complex equations, solving the Hamiltonian with several terms, etc. And then you showed this interesting example of the satellite and the artificial satellite going to the moon, or orbiting close to the moon around Mars. And then and then you showed solutions that to the first order would be fine and would be safe enough to guarantee that those both objects wouldn't crush, right? Wouldn't collide to each other. But what if, for instance, a meteor passes close by, and then you add, a fourth body to your system, a temporary one, but enough to remove this, equilibrium, this very, very tiny, delicate equilibrium that you have there. And then because your solution is not exact, but even it were exact, then you have this fourth body. And then how to solve this problem if you are here in the Earth, and then you have this satellite orbiting, and then you have to, you introduce like a chaotic solution, so you have to deal with these coefficients, new solutions. How to solve this non-classical? I mean, it's classical, but a non-linear process. I was wondering, how do you deal with the, because in real life, I suppose that there are these these extra external bodies, coming into your anybody's system all the time, right? Also around the Earth. So how to solve these challenges, these problems?
Thank you, Elizabeth, for your question. A very good question, by the way. I can explain how you obtain this, and you understand the limits of application. What helps us, for example, in order to get a linearization of those equations, so we expand all those terms in Taylor series and you get the first order term. The assumptions we make when we're expanding, let me show you. For example, I can give an example. We have, if you observe here in the linearized equations, we have the eccentricity. When I talk about expansion, I didn't define, sorry about that. We expand in terms of eccentricity of the orbit, so the shape of the orbit. So what does that mean? We are using perturbation theory. And in perturbation theory, we consider that we have a major term, a dominant term, and you have a small perturbation in the system. In our case, this small perturbation, and what we guarantee that is small perturbation? We have usually, when we look to the theories, we have epsilon, that is parameter that guarantees that the perturbation is small. In our case, this epsilon that is small is the eccentricity, because the eccentricity of Phobos is almost circular, is almost zero, so it's a very small parameter. So MMX, we need a slightly higher, don't need a big eccentricity. So even though the orbit, the eccentricity of MMX will not be so elliptical. In this case, we guarantee that when we perform the expansions of the equations of motion, what we're guaranteeing here is that these terms that carry eccentricity, they are small. And what we made with all the other terms that have eccentricity square, eccentricity to the third power force, we removed all of them. These are the terms that are negligible. And what will happen? When we remove all these terms, we are able to decrease the degrees of freedom of the system, and then we are able to integrate mathematically the system of equations. So if we have an object crossing the system, this object possibly is with a higher eccentricity, and would be a different type of model. But even though if there's a collision of this object will change abruptly the eccentricity of the satellite or Phobos. What will happen is this approximation, if the eccentricity increases significantly, what is very difficult to happen, this approximation is no longer applicable. What would happen, implied, is the quality of this, the quality of this approximation, instead of 1 mile after 1 month of evolution, what would happen would be tens, hundreds, or even thousands of kilometers of difference, because the linearized term, the first order term is no longer dominant, because we're considering that the perturbations of Phobos are small. in the object, in the spacecraft around it. As we could consider, the perturbations of the Earth over cumuleva are small, and the dominant term that is moving both cumuleva and the Earth is the Sun. It's a similar dynamics. So in this case, if we increase significantly the centricity, that is the case of a crossing object in entering the dynamics and trying to model independently, this modeling would not be efficient. Of course, we can numerically solve the problem. But the idea is we want to find these mathematical solutions for the problem. And we will not be able to predict this because this is only possible because we solve mathematically the system. But the condition for that is that the centricity and the perturbation is small. If the perturbation grows, the linearized model is no longer good, so the solution we obtain from that is not good. It's not accurate. So we have some constraints of application for this. So this extreme case where centricities are big or the masses are big, so the perturbation also grows. We need to use other techniques to deal with this type of problems. I don't know if that answers your question, but the thing is, this will not work for that type of challenge. If a big perturbation comes or the centricity is very big, because that will put close approaches, the gravity and perturbation would also increase. Potentially, Mars would even maybe potentially removed from the system if you pass too close, because you get so further from Phobos. Right. Then maybe if Mars, okay, you came here, you don't go back there. So I keep you with me. Yeah.
Right. Okay.
Yeah. We want to maintain it close. That's also mission wise comment. We don't want big eccentricity because we want to maintain as more circular as possible, close to Phobos. If we get eccentric orbits, we get further because the centricity will make the two objects get further. We want to maintain the most time as possible to make the most observations, and also it will be much easier to be in a more stable almost circular orbit, because from almost any point you can project the landing. If you are in a more elliptical orbit, you have moments where you're closer, but there are moments that are further. So you cannot make the maneuver to land on the surface of Phobos so easily, because you have the distance to Phobos is changing all the time in the elliptical orbit. If it's almost circular, it's almost the same all the time. So you have different directions you can plan the maneuver. So there are other engineering challenges also. Right. And because the geologists want to guide the right landing sites, right? So they would be happy if we provide solutions that allow them to sample and observe closer more regions and get a more complete map of the surface and other spectrometric observations and other stuff they are going to use to study Phobos, radar and other stuff. Yeah, so there are reasons, engineering reasons, scientific reasons, but also mathematical limitations for the model. So there are constraints. That's why you need to use within this regime of assumptions.
Mm-hmm. Right. And how big are those satellites that of the mission that of the two missions, I guess, that you are involved in? How big are those?
Sorry, I forgot to put a photo of. It's like MMX is more or less my size, twice my size.
Right. Mm-hmm.
So 3 meters maybe tall. I saw a model that is half. The size is more or less my size, and it's to here. So maybe it's twice. Then maybe from here to the wall you have here. So it's significantly big, because MMX will carry a lander from the German Aerospace Center, that is the German Space Agency, and that is the OR, and also that is being projected together between the Germans and the French, the CNES, the French Space Agency. So apart from the spacecraft going there, sucking the dust and particles from the surface, it will also launch a lander like Rosetta mission did with 67P Churyumov-Gerasimenko comets to investigate the surface of Phobos. So they are finishing the development of this. They are shipping soon, I think, to Japan. And the mission was planned to be launched this year, so everything is almost done. So, but now we have 2 more years with the delay of the launch to perform more investigations and double checking everything more efficiently. So we are excited and I hope you be interested, and there are many stuff to be done. People from geophysics, chemistry, planetary science, everyone is interested to understand this. Phobos will help us to finally understand the history of Mars and the solar system.
Okay, congratulations and good luck. I mean, we are all in the same boat.
Thank you.
All
And
the
thank you for
success.
having me here. It's a pleasure. Also, I need to tell you, this is the first. USP is also important in my life because my first date with my wife was here. So as she was studying here her PhD, I came visit her, became friends, and now we are together. Yes.
Thank you. More question? The last one, okay.
Do you think the samples, the results of this mission of MMX will be of interest in the study in astrobiology?
Definitely, because understanding, imagine if there was any type of bacteria there, and if Phobos is the result of a collision. Actually, this is why MMX is, I need to sell the product. It's more interesting than Mars and Return mission from NASA, because we have curiosity on their mission. They are collecting one area specific, the Anken crater. I forgot the name of the crater. But if there was this giant impact in the northern hemisphere of Mars, so pieces of Mars from many parts of Mars were expelled in the atmosphere, in the outer space, and they got together. So potentially in this case, Phobos contains parts of several areas of Mars. We can perform a more generic search for water and chemical elements, and can understand better the different areas of Mars, because a giant impact would remove dust and particles from different areas. So the sample from Phobos is more complete than just a limited crater that our partners NASA are bringing. They're great. But Phobos can provide more samples from more different areas in Mars. And so in this sense, potentially, imagine there was only bacteria in this part, but you cannot never discover if you're sampling the other area. But in Phobos, maybe you can find samples from, not here, but we find another one. Water and other stuff that are important in terms of think about life. But then we go to the philosophical questions, and yeah.
Thank you again.
Thank you. Desculpe. Sorry again for all the technical problems here. I want your feedback.